This is Honors Geometry, section 7.3 on similar triangles. And we're going to look at the three different methods to prove that triangles are similar to each other. Our first one is AA similarity. So we have two triangles. If we have one pair of corresponding angles and a second pair of corresponding angles that are congruent, what that means to us then is that the triangles are similar to each other. Next one, if we have all three pairs of sides that are in the same ratio, then the two triangles are similar to each other. In other words, we'll give these names: triangle ABC, triangle DEF. If the length of AB divided by DE is in the same ratio as the length of segment AC divided by DF, and those ratios are also equal to the length of BC divided by EF, then the triangles are totally similar to each other. And our third and final method of proving two triangles similar is side angle side similarity. So we have these two sides that are in the same corresponding ratios as the other sides of the other triangle. If the angles between them are congruent, that means that those triangles are in fact going to be similar to each other. So our question here, which triangles are similar to each other? Write the similarity statement and then tell why they're similar to each other. So I see two different triangles here. We have this triangle that I'm highlighting in yellow, as well as this triangle that's being highlighted in turquoise. And what I see between those two triangles is that we have one pair of corresponding angles congruent, and that by itself isn't enough. However, they both have angle C as one of their angles. So what I'm going to do is draw out the big triangle, the one that's in turquoise. It's triangle AEC. We have the double marking and the single marking. And right below it, I'm going to draw the yellow triangle, and I'm going to put the corresponding marks in the same location. So this is C, and the yellow triangle, angle B, is the one that has the single mark on it, and there would be angle D. So as I look at those two triangles now, I can see, yes, they are similar to each other. Triangle ACE is similar to triangle DCB, and a reason would be angle-angle similarity. In our next example, we're trying to solve for x, and we'll use that previous example as a guide in how to do this one. Once again, there are two triangles. We have a pair of angles that are marked congruent. They also both have that angle at the top as part of the triangles, and that's going to be part of the key in solving this one. So I'll draw this top triangle again. We have lengths of 5, 5, and 6. Then I'll draw out the entire triangle so that it looks like it's in the same orientation, the same markings. And let's see, between the double angle and the single angle in the whole entire triangle is that length of 9. Across from the single arc mark in the big triangle is 6 plus y. And then in the big triangle opposite the double marking would be the length of x. So now I'm going to look at the different corresponding parts based on their locations. And this is going to help us set up a proportion. The good one is the green setup that we have. That's 6 over 9. We have both of those numbers. And we can set that equal to 5 over 6 plus y. 6 over 9, why not simplify that to smaller numbers, 2 over 3? Now when we cross multiply, we get 15 equals 12 plus 2y. So y equals 3 halves. There is one answer for us. And then for the turquoise ones, we use the same proportion with the greens, 6 over 9, which we said simplifies down to 2/3, and that's equal to the turquoise of 5 over x. So now when we cross multiply, 15 is equal to 2x, divide both sides by 2, and x equals 15 halves, which would also be 7.5 or 7.5. But there are two answers for x and y. We'll look at another problem out of this section. We're given that 3 points are collinear. We have the coordinates for A, B, and not the entire thing for C. But if these points are all collinear with each other, that means that the slope from A to B to C is going to be consistent. So we can calculate the slope of segment AB, 12 minus 8 over 5 minus 2. So there is a slope going from A to B. And that's going to be equal to the slope from B to C. If we calculate the slope from B to C, that's 13 minus 12 over D minus 5. So here's what we've calculated for the slope to be equal to. That's what we know it's supposed to be equal to. So if we set those equal to each other and then cross multiply, we'll get 3 is equal to 4d minus 20. Add 20 to both sides, and then divide by 4, so d is equal to 23/4. Real quick check of that to make sure that it makes sense. This slope is going up from left to right, so since point C has a higher y value, the x value should be farther to the right, and 23/4 is, so I'm pretty confident that answer is correct. All right, here's our next example. We have three variables, x, y, and z, and we have this segment down the middle is perpendicular to the top and to the bottom. So with a perpendicular transversal converse, I know that the top and bottom must be parallel to each other then, which means that alternate interior angles are equal. So I can put some markings to show those angles are equal. Vertical angles are equal to each other. In other words, I have plenty of information to get that triangles at the top are similar to triangles at the bottom. And I'm going to start by looking at this entire triangle compared to that entire triangle. Now the orientation kind of switches. In other words, this segment, or this angle, the double angle marking is corresponding to that one. The single angle is corresponding to that one. And that's going to help me set up the proportion. Now one thing I know is that this entire length of 9 from the top one is corresponding to that length of 12. And then again from the top one we have a length of x. And that x is going to correspond to 20/3. Now 9/12, why not simplify that down to 3/4, work with smaller numbers. Cross multiply, 4x is equal to, when we multiply that we get 20. Solving that we get that x equals 5. So there is one of our answers. We're still looking for a few other ones. And I'm going to plug in that value of 5 and now look at a different set of triangles that are going to be similar to each other. And at the top we'll look at this triangle, and at the bottom we will compare it with that triangle. So as I look at that setup, I see that the 5 is corresponding to 20/3, so 5 over 20/3, and that's equal to this length, which I don't know yet, over y. Now in this triangle, because it's a right triangle, I have a leg of 4, hypotenuse of 5, I can use Pythagorean theorem or recognize that it's a Pythagorean triple. 3 squared plus 4 squared equals 5 squared. So it's going to be 3 over y. Cross multiply, 5y is equal to 20, which means then that y is equal to 4. So there's our second variable solved. Now I know that y equals 4, that's a little bit more specific. And the last thing we're going to do is solve for z. And to do that one, we'll look at another pair of similar triangles. Those triangles are similar to each other from the top to the bottom. 3 is corresponding to 4, just as this length is corresponding to z. I don't have this length, but I can use Pythagorean theorem. And it's not a 3, 4, 5 this time. If we use Pythagorean theorem, 3 squared plus 5 squared equals this squared. That's 9 plus 25, which means that this is the square root of 34. Now when we cross multiply, 3z is equal to 4 root 34. Divide both sides by 3, and we get that z is equal to this irrational number of 4 root 34 over 3. All right, next examples. Are the triangles similar to each other? Do we have any similar triangles? In this first example, we have a pair of angles that are congruent, so we have an angle. And then for the triangle on the left, 6 is the biggest length. And for the triangle, I'll put 2 marks because it's bigger. And for the triangle on the right, 20 divided by 3 is 6 2/3, so 8 is the bigger one. So when we're setting up these proportions, for the triangle on the left, we're going to compare the 6 with the 8. And then for the smaller lengths in this potential side angle side, 5 is going to be compared with the 20/3. So when we cross multiply, 8 times 5 is 40. 6 times 20/3 is also equal to 40. So yes, those proportions are equal. So by side angle side similarity, yes, those triangles are similar to each other. And the next setup, there's actually 3 sets of triangles. We have triangle 1, triangle 2, and triangle 3. Clear out a little bit of space here so we can look at those a little bit better. I'm going to put a single mark on this angle and a double mark on that angle. I don't know if those angles are congruent or not, but they are different. But if I focus in on this triangle right here, I know I have a right angle because it's a linear pair. And also, this single mark and that double mark have to be complementary to each other. If I just focus on the entire triangle, in the big triangle we have 90 degrees, so those two are complementary. And then if I go back and focus on this triangle right here, it's another right triangle. This is complementary with that angle, which means that measurement has to be the same. And if I focus right here, the double and the single angles are complementary to each other. So since this is double, and we have an entire right angle right there, that means this has to have the single marking on it. Now if I compare all three of those triangles, I see they all have a right angle, they all have a single arc marking, they all have an angle with a double arc marking on them. So not only do we have angle-angle similarity, we have all three sets of angles. So once again, we have yes by angle-angle similarity. Plenty of information to get that all three of those triangles are all similar to each other. In our third example, we have parallel lines, parallel segments. The vertical angles are going to be equal to each other. The alternate interior angles are equal to each other, so I can stop right there and say yes, for sure, those two triangles, the one at the top, the one at the bottom, are going to be similar to each other. Okay, we're going to look at a couple more things. First one is called the triangle proportionality theorem. And I see this entire triangle, and then there's this segment going across the middle that's parallel to that bottom side. And because it's parallel, we know that corresponding angles are equal. So I can put those little markings on there. And what that means to me then is not only do they share this angle at the top, but all three pairs of angles in this little triangle at the top compared with the entire triangle are congruent, so the triangles are similar to each other. Now using that fact, we can then say that the corresponding sides must be in the same proportion. If two triangles are congruent, then all the corresponding sides and all the corresponding angles are congruent. However, when triangles are similar to each other, all the corresponding angles are still congruent, and we do have that already, but all the corresponding sides are in the same proportion. In other words, go back and do a little bit of highlighting here. For the triangle on the top, we have a length of x. X is corresponding to this entire side in the big triangle, or x plus y. Looking on this other side, we have that A is corresponding to A plus B. So that's true because the triangles are similar to each other. Now if I cross multiply here, we get AX plus BX, and if we multiply in the other direction, we get AX plus AY. Interesting thing here is that AX is on both sides, so I could subtract. And now what I'm going to do is actually divide again. I'm going to divide both sides by Y, gets rid of that, and also divide both sides by B to get rid of that, and we end up with x over y is equal to a over b. In other words, because of these parallel segments, we got that x over y is in the same proportion as a over b. We don't have to use the entire sides of the triangles in this case. Now a note on this one, x over y equals a over b. That is not equal to c over d, because it's equal to those other fractions, those other proportions. The blue proportion that I have here was because the original triangles were similar to each other, which would also make it equal to c over d. However, these two things are clearly not equal to each other, so c over d can't be equal to both of those fractions, and in fact it's only equal to the one at the top. We've talked about the midsegment theorem before, but we'll just revisit it right now. So if we have triangle ABC, if I find the midpoint of segment AB, we'll call it X, and the midpoint of segment AC, we'll call it point Y. And then if we draw in the segment that connects those 2 points, we have a midsegment. And because this over this is equal to this over this, AX over XB is equal to AY over YC, this isn't a 1-to-1 ratio, that's in a 1-to-1 ratio, then I'd be able to get that those sides are parallel, these segments are parallel to each other, which we already talked about before. And then, because AX over AB is in the ratio of 1 to 2, that's how I know that this midsegment divided by BC is also going to be in the ratio of 1 over 2.